Welcome you are. Today we discussed how to design a PI controller. So before going to design, just know one thing. Before we start designing, we have to clear one concept, is that if this is our S-plane, okay, so this is my sigma and this is j omega. For example, if I have a pole here or any point here, so if I just drop down, so this distance is normally, if I represent this distance by sigma of d, so this point is minus sigma of d. This minus sigma of d is normally equal to, in second order, as sigma omega n. So similarly, this point, if I draw a line to the origin and this length is omega n, and this angle, if it is omega theta, so in that case this point is j omega n under root 1 minus zeta square for second order, or I can write it as omega j omega d. So how to calculate j omega d? Because this is a 90 degree, this is a theta, so we know that this angle is actually equal to cos inverse of zeta. So from here we understand that omega d, which is this side, okay, omega d is actually equal to because we have to apply the tan theta, that means you have a perpendicular divided by base. So if I multiply with base, it becomes phi of d, this is the length, and tan of theta of this theta is equal to cos inverse of zeta. So this is the way you can find the location of this point. So this is important before starting the design. Now in this video we normally we design PI controller. So if you remember how PI controller look like, if this is k of s, it is equal to k1 plus k2 divided by s. Right, so this is the controller. Now I have to design, basically I have to find the values of k1, k2. How I do that? Let's consider plant here, and plant dynamics are 5 divided by s plus 3 and s plus 8. So this is the system for which I have to design a PI controller with specification. So why I have to design a PI controller? Because they want zero steady state error for step input. This is one criterion. So from here we know that we have to go for PI control. Next one is overshoot, and he is asking that overshoot is MP is less than 0.057, or in other terms it can be written as 5.7%. So this is the second criterion, and the last criteria is that settling time, if I consider 2% criteria for settling, is must be less than 0.8 second. Now from here we first of all we have to find a desired point where we want to put our root locus, or want to put our closed loop pole. So for that reason we use these specifications. So from this specification, first one, we know that MP, which is equal to 0.057, I can calculate the zeta from here, and if you remember, the formula for zeta was log square of MP whole divided by log square of MP plus pi square. So this is the formula. When I put the values in this formula, so if I quickly do that, this is log square of 0.057 divided by log square, this is natural log actually, okay. square plus pi square. So when I solve this, I come up with value of 0.674. So the first criterion I know for the standard equation is that zeta is 0.674. Okay, so I know the zeta. Now I move to next one. Next one is settling time, and settling time for 2% criterion is 0.8 second. So it's actually less than 0.8 second. So this implies that if I remember, the formula of settling time is 4 divided by sigma d. So from here we can easily calculate the sigma d must be equal to 4 divided by 0.8 in this case. Okay, so it is around if I solve it, it becomes 5. So I get two values. If you remember, I start with the point in previous slide, so I need two values for this desired point. One is sigma d I calculated, and the other is zeta. So this zeta will use to calculate omega d. Now I am going to calculate the desired point, and desired point is, now I know sigma d. Now I move to omega d so that I can calculate the desired location. So omega d is equal to sigma d tan of cos inverse of zeta that I just calculated in previous slide. So it becomes, this implies that omega d is equal to 5. This from here, tan theta of cos inverse of zeta. Zeta values was 0.674. Now when I solve this, it becomes 5.55. So this means that the desired closed loop poles are S1, S2 is equal to sigma d plus minus j omega d. That becomes 5 plus minus j 5.55. So from here, now let's pick a design point. Design point, assume, call it a P1 is equal to, say, so this must be a minus. Okay, this is minus 5, okay, plus 5.55 j. This is my design point. Now if I quickly plot the root locus here, so if you remember, this was my plant at minus 3 pole, at minus 8 pole. So this is minus 5 point, and assume, so this is the point where we want our location. So this point is actually 5.55 j, right? So here I want our closed loop poles. Now before designing it, if you remember, we have a characteristic equation that has 1 plus k of s, g of s, h of s. If you remember, this is the characteristic equation. So we do it in MATLAB based on this characteristic equation. Here we want to design a PI controller, so this k of s becomes k1 plus k2 divided by s. Okay, so I can rewrite it as if I take k1 out, it becomes s plus k2 divided by k1. Okay, if I take k1 out, so it becomes 1 plus k2 divided by k1 sorry, make it 1 times s. All right, sorry about this s. Okay, now this is another form. Now if you remember, g of s was 5 divided by s plus 3 and s plus 8. Now from here we know that if I put these two equation here, it becomes 1 plus 5 times k1, okay, and if I take s out, so it becomes 5 times k1, 1 plus k2 divided by k1 s whole divided by s plus 3 times s plus 8, or I can rewrite as 5k1 s plus k2 divided by k1 whole divided by s times s plus 3 and s plus 8 plus 1 is equal to 0. Now this is a characteristic equation. If you remember the criteria that we normally use to design, we say that there are two criteria. First one is the magnitude one, that k of s, g of s, h of s, if it is available, in our case is 1. Second criteria is the angle one, that you have to find k of s, g of s, h of s is equal to minus 180 degrees. So these are two criteria based on which we will try to design our controller. Now before designing controller, let's plot the root locus here, and this is very important point here. So if you remember, we have here is the pole at minus 3, here is the pole at minus 8, right? Now I just change the color. I know that pi has one pole at the origin and another 0 here, okay, so I call it this location as pi. Similarly, this location as zpi, okay. I need to find this location. Now I choose a black color, and from here, as we know that this is minus 5, and we make this our closed loop pole desired location. So this was 5.55 j, okay. Now to we pick this angle 1, and to find the angle, what we do here, I just draw a straight line here. It make a 90 degree. So I draw a line, this pole, another line, this 0, another line with the system pole, then another line with second poles of them. Now I make a different color here. This is my phi 2, okay, this angle. I make this angle as phi 1, right? Now I use a different color. Now I make this angle as phi of z pi, and I make this angle as phi of p pi, okay. Now as we know from this equation, so if I write the what you say angle, so what I know that we have minus phi 1, minus phi 2, and we have plus z pi, then we have minus phi pi is equal to minus 180 degree. Now we have to calculate the angle. Now we use trigonometric variation, that we know that this height is known to us, that is this one 5.5, and this so for example, if I want to calculate phi 1, okay, so I write here for phi 1, okay, this is equal to, now this is phi 1 because if I consider this triangle, okay, this triangle, if I consider this triangle, this one, okay, so this angle is actually equal to because whole angle is 180, so it is 180 minus 10 to solve this triangle. So to solve this triangle for this theta, okay, I just minus it. So for this theta you have this perpendicular divided by base, so this is equal to tan of 5.55. this is perpendicular value, minus you have 5 minus 3. So this is the way you can find the theta 1, phi 1, okay. So this becomes 110 degrees. Similarly, to calculate phi 2 is this one, so you have to consider this triangle. You have to consider this triangle, okay. So from here now we have to use direct tan theta, because there's nothing minus in this case. So I say that, okay, so this is actually tan inverse for calculating this, sorry about that. So this becomes tan inverse of so you have this perpendicular divided by base. So perpendicular is again 5.55, so base is 8 minus 5. So this becomes, when you solve this using your calculator, it becomes 62 degree. Similarly, now I calculate 5 PI, that I can do it, because this is again I have to use 180 degree minus tan inverse. So how I can, so this is I am looking for this theta. So for this theta, so what I can do, I can take this whole triangle, it's a right angle triangle. So height is given to us, again this is 5.5. so height is very simple, 5.5 divided by is 5 minus 0. So when I solve this, so this angle becomes 132 degree. No, I just put here, it becomes minus 110 degree. This becomes minus 62 degree. I don't know the phi of z pi, minus I know 132 degree, so it becomes minus 180 degree. From here, phi of z pi becomes, if I solve it correctly, so it becomes 123 degree. Now still I know this angle, so this angle is known to us, but I don't know about this location, this is unknown. So how to find ZPI? So what I do, I use the same method that I use for, so I say that, okay, I consider this triangle, I say, okay, Z of pi is equal to, because this is again 180 minus, because this is 180, so I have to consider this angle. So this is 180 minus, so this is again, the height is given to us, tan inverse, that is 5.55 divided by I know this is 5, I don't know this value, so I put 5 minus z pi. So this must be equal to, from this, 123 degree. Okay, now when I solve this, so I easily calculate ZPI is equal to 1.34. Okay, now I know the location of 0, okay, I know the location of poles. So from here, because in pi, what I say that pi is equal to, that is k of s is equal to, if you remember, I wrote like k1, I say s plus k2 divided by q1 whole divided by s. Alright, now this is equal to this 0, this value, okay, this value is equal to this one. Now this means that what I designed till now is k of s equal to k1 s plus 1.34. 1.34 whole divided by s. Now I have to find k1. Okay, how I find k1? Now I use this condition to do that, so I need to move to next slide. So k of s known to us is that k1 s plus 1.34 divided by s. Now for finding k1, I have to use the magnitude, that is k of s, g of s, h of s must be equal to 1 at point that I choose, that is p1. So if you remember, what was the p1? P1 was minus 5 plus 5.55j. So I just put in here. So from here we know that I just put the value here. So it becomes k1 s plus 1.34 divided by s times the plant was 5 divided by s plus 3 times s plus 8. Now take the magnitude is equal to 1. Okay, I have to evaluate at p1. So we can rewrite it as k1 at s equal to p1 must be equal to just do a little manipulation. It becomes 5s s plus 3 and s plus 8 whole divided by k1. Sorry, there's no 5 here, sorry about that. I just have to cross multiply. This becomes on top, this is in denominator, so it becomes k1 5 times s plus 1.34, but evaluate at s equal to p1. So just put in the values of s, that is minus 5 plus 5.55j. so again put here minus 5 plus 5.55j plus 3. Similarly we have minus 5 plus 5.55j plus 8 whole divided by k1 5 minus 5 and plus 5.55j plus 1.34. So as you know that to take the magnitude you have to square the real part, and imagine when you do that you come up with a value of k that is equal to 8.36 after doing all the calculations. Now after getting this, we know that we design our PI control as k1 s plus 1.34 whole divided by s, that becomes 8.36 times s plus 1.34 whole divided by s. So this is the answer. This is the way you can design your PI control. Thank you.